Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for physics. This is lecture number 5 of alternating current. So let's begin with today's class. In today's class we are going to discuss about the transformers. So let's begin. We can say that transformer is a device which transforms the electric current from one circuit to another circuit with same frequency. This is important that frequency remains the same. We can say transformer is a device which converts low alternating current at high voltage into high alternating current at low voltage and vice versa. So indirectly this has been said that even the power remains the same. If you do not understand this, let's have a look at this, which converts low alternating current at high voltage into high alternating current at low voltage. Yes, so P is equals to VI. So the power on both the sides will remain the same. Next, let's look at the construction. Let's look at the construction and working of transformer. It works on the principle of mutual inductance, that we are having two coils, coils with which uh, supply has been connected is called as the primary coil. So this is the primary coil, and another coil with which output is being collected, or certain devices has been provided output from this coil. This is what we call as a secondary coil. It is also called as the input coil, and this is the output coil. So we can say a transformer consists of two sets of coils insulated from each other, and they are mounted on a soft iron core as shown in the figure. This is the soft iron core, as we can see this. One of these coils are called as the primary coils or input coils, and let's suppose it is having an NP turns. It's a number of turns in the primary coil. And the other coil is called as the secondary coil or output coil, and it is having ns number of turns. It's a number of turns on the secondary coil. So we can say that when an alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links to the secondary and induces an EMF in it. That means when current flowing through a coil or magnetic flux link with a coil changes, and induce EMF in the other coils. So let's suppose understood that phi be the magnetic flux in each turn in the core at time t due to current in the primary coil, when an EMF or voltage EP or VP to apply to it. So according to the Faraday's second law, we can say the induced EMF or voltage in the secondary coil with ns number of turns can be written as this: ES is equals to VS is equals to minus of ns into d phi by dt. This the alternating flux also induces an EMF which we call as a back EMF in the primary coil, and this could be given as this is EP is equals to minus of NP into d phi by dt. So if I take a ratio of this two, it's an ES is to EP, which is equals to VS by VP, or I should say NS by NP. In a reality, it's a NS d phi by dt minus NP d phi by dt, but we understood and we mean that its rate of change of flux will remain the same. So d phi by dt will remain the same, and if d phi by dt will remain the same, this is equals to ES by EP. This is equals to VS by VP, that is equals to NS by NP. So this VS by VP or NS by NP is called as the transformer ratio. For ideal transformer, when I say it's an ideal transformer, that means the no energy is lost in the process of transformation. We can say P output or P input could be equals to VSIS, or it would be an VPIP. And this transformer ratio, the ratio of this transformer, it's in Vs by Vp. That would be equals to Ns by Np or Ip by Is. So the ratio of number of turns in the secondary coil, the ratio of the number of turns in the secondary coil to primary coil is called as the transformer ratio. And transformer cannot work with DC voltage because on the primary side number of a coil having number of turns has been attached, and it works on the principle of Faraday's law. So if current is not going to change, no EMF is induced, and so there would be no output on the secondary side. So it cannot work with DC voltage. If you want your transformer to work, you must and you needed to connect it with the AC only. Now let's discuss the types of the different transformers. First is the step up transformer, and when I say step up transformer, I must understand that number of turns on the secondary would be greater than the number of turns on the primary. So step up transformer will convert a low AC voltage into a high AC voltage. So this is the transformer, and this is the primary coils, this is the secondary coil, and it will be this is the potential on the primary side, this is the potential on the secondary side. So the situation will be it convert a low AC voltage, that means Vp would be less than Vs, but in this case Ip would be greater than Is, because power remains same. You should keep in mind this, that if you want to change the voltages, that you want that on the secondary side there should be a higher voltage than the primary side, then you are going to increase the voltage. But when you are going to increase the voltage on the secondary side, you are ultimately going to decrease the current in the secondary side. Next, it's a step down transformer, and in this case NP is greater than NS. You can see this, that number of turns in this coil is greater than number of turns in this coil. So these are the primary windings having NP turns, and this is the secondary winding having NS turns. So it converts high AC voltage into a low AC voltage. So you can see this, or you can see this, it's a voltage on the primary would be greater than the voltage on the secondary. But it even means that it's a current in the primary will be less than the current on the secondary because power remains constant. I hope you understand this. Do you? Do you have any doubts? Is there anything? Is there anything? No? Great. Now let's discuss the efficiency of the transformer. When I say efficiency, it's a ratio of the output power to the input power multiplied by 100. This is the efficiency, and this would be equals to VSIS divided by VPIP multiplied by 100. For an ideal transformer, this efficiency would be equals to 100 percentage, and so that output power should be equals to the input power. This is the efficiency of a transformer. I hope this is clear. Is it clear everything? Up to this, does it clear? Are you sure? Are you? So, can you do the numericals based on this? Can you? Great. Let's have a look. Work for the numericals. Suppose the question says that a transformer is having efficiency of 90 percentage, is working on 100 volt and 2 kilowatt power. If the current in the secondary coil, if the current in the secondary coil is 5 ampere, calculate first the current in the primary coil, the current in the primary coil. Second, voltage across the secondary coil. You require this too. So think what all have been given. They have said a transformer is having an efficiency of 90 percentage. Its efficiency, it's a 90 percentage. Is working on 100 volt. Is working on the 100 volt, and power would be of 2 kilowatt. It's a P, which is equals to 2 into 10 to the power 3 volt, and it's working on 100 volt. That means a voltage on the primary side is given, which is equals to 100 volt. Now if the current in the secondary coil, one more thing, it's an IS is given, which is equals to 5 ampere. Yes, this is the data they have given. The current in the primary coil, that is IP, is required, and voltage across the secondary coil, VS, is required. So first, how will I do this? What is to be done? So what I understand is VP, it's an, or I should say power is equals to VPIP. It's a total power is equals to voltage on the primary side multiplied by current on the primary side. Now the power given, it's a 2 into 10 to the power 3. Voltage on the primary side, it's a 100 volt, and current on the primary side is required. So IP could be given as, it's a 2 into 10 to the power 3 divided by 10 square. This has gone. So this is IP, it's a 20 ampere. Current on the primary side, this is equals to 20 ampere. Now I need to find out the voltage on the secondary coil. But before I calculate the voltage, that could not be easily P is equals to VSIS, because your efficiency is not 100%. Your efficiency is just 90 percentage. So first I need to calculate the output power. How could I calculate it? Let's have a look. It's an efficiency is equals to power on the output to the power on the input. So this is power on the output to the power on the input. This is 90 by 100. This is output power. Divide by input power. Now as I know that input power, it's 2 into 10 to the power 3. This has gone, this has gone, and this has gone. Only two terms would be remain. So output power could be written as, this output power could be written as 9 into 2 into 10 square, which is equals to 1800 watt. This is the output power. Now what you need to do is, you need to P output is equals to voltage on the secondary multiplied by current on the secondary. This is equals to 800 volt. This is equals to Vs into Is. uh, I don't know Vs, but I know the Is, which is equals to 5 ampere. So this is equals to 1800 is equals to Vs into 5, and from this I could have, it's a Vs, which is equals to 1800 divided by 5, which would be equals to 360 volt. I hope you get this answer. Have you? Did you receive the same? Did you? Are you sure? Do you have any doubts up till now? Is there anything? Do you have any doubts? Do you? Are you sure? Great. So ready for the next question? Let's have a look. The next question says that a step up transformer, a step up transformer operates at 230 volt line and a load current of 2 ampere. Ratio of the primary and secondary windings is 1 is to 25. What is current on the primary side? You need to find out the current on the primary side. How will you do this? So it says that a step up transformer is there which operates at 230 volt line. When it operates at 230 volt line, that means primary voltage has been given. Vp is 230 and the load resist and the load current of 2 ampere. That means the current on the secondary side is given. It's a load current. So when it's a load current, it's an IS. Ratio of the primary to the secondary, it's an NP is to NS, which is 1 by 25. What is the current on the primary side? How will I do this? What could be done? So as we know this that NP is to NS is given 1 is to 25. So this is equals to ES by EP. That is equals to it's a P is equals to VI. So this is IP is to IS. This is equals to NS is to NP. This is the relation. I hope this is clear. So this could be, if I equate this to, it's an IP is to IS. That is equals to NS is to NP. And I have been provided that NP is to NS. It's a 1 is to 25. That means NS is to NP. It's a 25 is to 1. IP, I don't know. IS, it's a 2 ampere. This is equals to 25 is to 1. So IP is equals to 25 2 it's a 50 ampere. I hope this is clear. Does it clear? Are you sure? Do you understand this? Have you got this? Great. So now let's discuss the energy losses in a transformer. First loss would be regarding the flux leakage. We can say that there is always some flux leakage, and that is not all of the flux due to the primary passes through the secondary due to a poor design of the core, or we can say the air gaps in the core. So this can be reduced by winding the primary and secondary coil one on the other. This will reduce the air gap, as well as this will reduce the losses in, because as it is a form of energy and that needs to be traveled through air only. So if we are going to wind it one over the other, this will reduce that losses. A second loss is the resistance of the windings. So we can say the wire used for the windings has some resistance, and so energy is lost due to the heat produced in the wire, and that loss could be considered as I square R losses. So in high current and low voltage windings are minimized. High currents, low voltage windings are minimized by using thick wire. uh, third loss is regarding the eddy current losses. We can say that the alternating magnetic flux Alternating magnetic flux induces eddy currents in the iron core, and it will cause a heating effect. This effect is reduced by the laminated cores. Is it clear? Is it correct? And last loss is the regarding the hysteresis loss. The magnetization of the core is repeatedly reversed by the alternating magnetic field, and when it is alternately reversed, the resulting expenditure of energy in the core appears as heat, and it is kept to a minimize by using a magnetic material which has a low hysteresis loss. Because if it is having a high hysteresis loss, it will loss of a large amount of an energy, and that energy cannot be linked to the secondary, and so on. Efficiency will be reduced. So these are some of the losses that has been attached while we are using the transformers. Now let's look at the next questions. What we understand by the whatless component of the current? Yes, the component of current which we call as an IRMS sin phi is the whatless component of current. Same way, what is the watt full component of current? So it's IRMS cos phi. IRMS cos phi is the watt full component of current. Do remember this. Next, what is the phase difference between voltage and current? What is the phase difference between voltage and current when the power factor in LCR series circuit is unity? The phase difference between voltage and current is zero, because power factor is unity, because cos phi is equals to 1, and it is the possibility when phi is a 0 degree. So, and we can say that phi is the phase difference between voltage and current. Now let's look at certain quick questions. First, transformers are used in DC circuit? No, they cannot use it. In AC circuit only? Yes. DC? No. Integrated? No. So transformers are used in the AC circuits only. Next, the magnitude of the EMF across the secondary of a transformer. The magnitude of the EMF across the secondary of a transformer does not depend on, first, the number of turns in the primary, the number of turns in the secondary, the magnitude of the EMF applied across the primary, and the resistance of the primary and the secondary. Yes. So it depends. As you can see, this is the ES divided by EP, that is equals to NS is to NP. Yes. So number of turns in the primary, it definitely depends. The number of turns in the secondary, it even depends. The magnitude of EMF applied across the primary, it depend on this, but it does not depend on the resistance of the primary and the secondary. So this will be the correct answer. I hope this is clear. Next, the transformer ratios for ideal transformer is, yes, it's a Vs by Vp, that would be equals to Ns by Np, and that would be equals to Ip is to Is. I hope this is clear. Is it clear? Great. So let's just winding up this session over here. This was all about the transformers. Please go through this once, and this will be yours. Thank you. Have a good day. Take care. Bye.